In this video, we discuss about vectors, how vector components transform under coordinate transformation, and also we define a dyadic product of two vectors and a second order Cartesian tensors. So consider a rectangular right-handed Cartesian coordinate system. Let E1, E2, E3 are the basis vectors along the three coordinate axes. Any vector, here it is A, can be expressed as a linear combination of these E1, E2, E3 basis vectors. The magnitude of the vector of this vector is determined by taking the sum of the square of the coefficients of the vector along the basis vectors. The scalar product of two vectors is defined as taking the product sum of the product of the components of the two vectors along the basis vectors. The vector product of two vectors is defined through Levi-Civita symbols and the component of the two vectors which is given here. Now let us discuss how components of a vector vary under translation of the coordinate system. We have a coordinate system with origin O and another coordinate system with origin O prime. The origin O prime is related to origin O by a position vector x naught. A vector corresponding to the coordinate system with origin O and can be related to the same vector in the coordinate system with origin O prime by this relation. Here the basis vectors are unchanged, so it's easily represented with a just a position vector of the two coordinate systems. So let's take the scenario where the basis vectors change from one coordinate system to another. So then we write a new basis vector for another system. So let's take one coordinate system is rotated with respect to the other, with both of them have the same origin. So a vector is expressed in both coordinate systems. So both coordinate systems have two different basis vectors, E1, E2, E3 for the original, E1 bar, E2 bar, E3 bar for the new coordinate system. So we now construct a matrix by taking dot product of the basis vectors of the two coordinate system. This matrix transforms from the this matrix relates the basis vectors from one coordinate system to the other coordinate system. So this matrix turns out to be orthogonal, so one can prove this relation. So this matrix M is an orthogonal matrix. So the components of the vector of a vector in two coordinate system is related through this matrix M. So if we admit only rotation, then this matrix is an proper orthogonal matrix. If we consider a transformation from right-handed coordinate system to left-handed coordinate system, then the matrix M will be improper orthogonal matrix. The vectors which transform under improper orthogonal matrix are called as pseudo vectors. The scalar product of two vectors is invariant under the choice of the coordinate system. One can prove that result. The vector product of the two vectors is also invariant under a transformation, but the transformation should be proper orthogonal matrix. So the M should be determinant of M should be 1. That defines M is a proper orthogonal matrix. Now we will define what is a dyadic product. a dyadic product of two vectors A and B is written with this symbol, and it has the properties, it has some scalar, it has the properties that scalar, first one, it is a scalar multiplication of a parameter with a vector and taking the dyadic product with another vector is equivalent to taking the dyadic product and then multiplying with the scalar. And the next one is taking a dyadic product of a vector with the sum of the two vectors is equivalent to the sum of the dyadic product of a vector with two other vectors. So in terms of components, the dyadic products can be expressed using unit these vectors are called as unit dyads constructed from the basis vectors. So a dyadic product can be expressed in terms of linear combination of unit dyads. One can show that the dyadic product of A and B is not equivalent to dyadic product of B and A. And also the dyadic product is independent of the choice of the coordinate system. So this result, so we can see from here the dyadic product of A and B and the dyadic product in one coordinate system is equivalent to dyadic product in the other coordinate system. So dyadic products, it has dyadic product, it forms an inner product with another vector. Just we take the inner product with the dyadic product, so you get the result A dyadic product B dot C gives A into B dot C. This is the result you get. And in terms of components, one can write this inner product. The concept of this dyadic product can be extended to more than two vectors. Now we'll discuss what is a Cartesian tensor. We'll define a second order Cartesian tensor. So it is expressed as a linear combination of unit dyads, and the components in two coordinate system, they follow the transformation law like this. In one, second order Cartesian tensor is related to the second order Cartesian system in the other coordinate system through two orthogonal matrices. This is the transformation law for the second order tensor. The interchange of indices here like A, Ij, and we can show that the A QP and A PQ are all same. So the interchange of indices are preserved under coordinate transformation. If Aij is equivalent to Aji, then this second order tensor is said to be symmetric. One can show that any second order second order tensor can be decomposed into sum of the symmetric and an anti-symmetric tensor, and this decomposition is unique. Thank you.